Okay, number one. So by increasing T from 80 milliseconds to 120 milliseconds on the spin echo or sequence, which of the following is the expected result? And there wasn't time for me to go through all the responses and see the questions that were more missed and the ones that were more answered. Could have been given the kind of idea to the structure of the questions that gave little difficulty. But in any case, I think by the end of this discussion, we would have gained some things that were not were not explicit throughout the lecture. Because of course, like I said, you can't get everything, even in 1 year or so. For those of us who want to specialize in MRI, we just take a little more time to get into some of these things. So by increasing TE from 80 to 120 atmospherical, which is the expected result? Is it A, pure protons, B, blah, 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 C, or D?
B.
Okay, straight away. That's B, because I will be better to contribute due to T1 relaxation. Because TE is greatly influenced by T2 characteristics of it. So if we, TE is influenced, T2 is influenced by TE parameters. To increase TE, T2 characteristic will be enhanced. So I don't think we should have any problem with it. So two, 6 successive 180-degree RF pulses applied following a one, which resulting echo will contain the greatest signal. Which echo? Is it the first or the sixth or the mid or the third?
Echo 1.
Okay, it should be echo 1.
First one. A.
Yeah, it should be 1.
The first echo.
Because the train, we follow the FID curve, the FID, the pre-induction decay curve, and the curve exponentially drop down. So at any point in time, the first, of course, we have the highest end signal, followed by the second, the third, and so on and so forth. So for 6 successive 180, following 90 because the earlier the better, or the earlier the more pronounced. Number 3, the frequency encoding gradient must be turned on during which of the following events? Is it phase, spin lattice, or readout of the echo, at the application of the RF pulse? Where must we turn on the frequency encoding gradient?
Read that time. C.
Actually, for we to be able to read out the signal, or sample the signal, it has to be the frequency encode has to be turned on. If you don't turn it on, then we won't be able to read it. So for 4, the information recovery sequences, TI, not T1, is the value of. We shouldn't have a problem with this.
Is D, sir?
Yeah, D, straight up, D. Between 180 and subsequent 90-degree pulse. 5, each line in case space is defined by blah, blah, blah. Which of these selections gives the right answer? Is it a phase encoding? Is it A, B, C, or D? Of course, there shouldn't be anything called D. D is out of it. You got eliminated G.
Well, I think I went for C. I don't know.
Okay. Each line for case space, each horizontal line
Okay.
in case space is given by the phase. Each horizontal line, while each vertical line is for the frequency. So
Yes,
the
sir.
first one, phase and coding gradients will give us each line, while each point, of course, because of each horizontal line will be given by a frequency. So frequency and each line, the line they mean here is the vertical, the horizontal line. So that will be phase and code. Even from that, we shouldn't have any problem with this, ideally, because we only have for A and C, and slide selection has got nothing to do with this. So even if you have a hazy knowledge about it, we might probably also go for C. So C. Which of the following parameter combination gives us a set of proton density when a spin echo sequence is selected?
I think I went for C. I don't know. The longer TR and shorter T.
Okay. Any other response? Do you have any other response? For T1 weighted images, we usually have a short TR and a short TE. Whereas for T2 weighted images, we normally have a long TR and long TE. But in between these two, proton density weighted image sequence appears, and it's usually acquired using a long MTR and a short MTE. So for both proton density and T2, we normally use long TR. For that of PD, proton density is not as long as that of T2 weighted image. For T1, the TR is always short, in the sense from around 300 to maybe 600, 700 milliseconds. Whereas for PD and T2, it starts from around 2000 milliseconds. Then for the TE for T2 is long, around neighborhood of 100 milliseconds. Whereas for T1 and proton density weighted images, they have them short TE from around 10 to 20 seconds. I mean milliseconds. So for this, it's clearly C. We clearly see 2500, which gives us a longer TR, and then 20 seconds, 20 milliseconds, gives us a shorter TE. We have been talking about a T2 image. It will have been this D. The question had been T2, it would have been this. And if it had been T1, we would have gone for this. But this TE is a little bit longer than what we normally have in TE. But if we still go for it, maybe if we had around 15 10 here, it would have surely been the sequence we would have been choosing if we wanted to go for a T1 with the image. So 7.
Hello, sir.
Okay.
Hello, sir.
I'm here.
Yeah, for that number 6. Now you said if it had been T2, it would have been D. Why can't it be B, sir?
Why can't it be B?
B, yes.
Okay, yeah. Can also be B. You can also repeat. You can also repeat.
Okay, sir.
Can also repeat, but mostly T2, TE for T2 is in the neighborhood of from 100. For this one, we still go for
Okay.
T2.
Okay.
Look at the following screen, pause sequences result in the shortest scan time. Of course, this is a giveaway question. Let's have B.
Yes, sir.
For 8, one disadvantage of fast brain pause sequence versus the conventional SC pause sequences. What I think this should also be a
C.
bonus. Yeah, decrease signal to noise ratio SNR. For 9, when performing a 3G gradient echo pause sequence, what determines the examination time? We have our NSA to be another signal.
I think I went for A.
A.
The number of MSA and the flip angle.
Okay. Any other, any contrary view? I went for A.
I went for A too.
Okay. Okay. I think most of us looked at it was A. But I think it's not A. It's actually D.
Okay.
The why it is not A is
Okay.
because of this 3D. Because we can use if I gradient echo for sequences, normally mostly used for 3D images, things like volumetric images, instead of just 2D. So because of that, we are not looking at, of course, flip angle has got some things to do, but evidently it is the number of slices that will affect the examination
Okay.
time at the end of the
Stand
day. Because you have so many slices you are dealing with. If it had been just one, then there wouldn't be need for number of slices because the slice is just that slice. But because we are dealing with a 3D gradient echo, so the
Okay.
number of slices will definitely because and again see of course the number of instrument of the use and and the number of steps because it's common to all of them. So
Okay, sir.
it's D.
Thank you.
But following 90 degree RF pulse, the signal created is what?
We can see it. Okay. This one.
What's the name of the signal created after a 90-degree frequency pulse?
This one wasn't straightforward, sir. Because only one. Because after the 90-degree pause, nothing was said about it again. Well, is it pre-induction decay or it can be T2? It can be great. Well, I'm not sure, sir.
Okay, in a question like this, I think the best bet is just to, if we don't actually know, just to try and then see how much we can eliminate. The more we are able to eliminate, the greater will be the probability of scoring the question, getting the score there. After we apply a 90-degree pulse and we leave the signal, and I mean we switch off and the frequency pulse, the 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 molecules or whatever the protons, they will now begin to relax based on both T1 decay and then T2 decay, spin realization and then spin of realization. So following 90-degree RF pulse, the signal that is created is a pre-induction decay signal, a signal that decreases with time. So from the top of, from the maximum of such a signal at each point, we now draw a T2 curve. And evidently, and also T2 star curve. The T2 curve is the one I will have shown it at the board. Okay, maybe I should show this on the board. Let me stop and then let me start the video now. It's a 90-degree, when we apply our pulse, a 90-degree pulse, we have, of course, at resonance, we have P0 or P1, whatever. But immediately we apply a 90-degree pulse, we have this move down this way. But so we have a maximum signal for T2. All the horizontal, the longitudinal have been transferred to the transverse magnetization. But immediately we leave that. Immediately we put off the signal. Immediately we put off the RF pulse. The signal will now begin to so this is the FID, induction decay. We can join the top of all this and give us our T2 decay. Whereas for T2 star decay, has decay because of the homogeneity and other stuffs. We have a T2 star decay. So it's actually the FID, not the T2. This is our signal. And the signal will continue to decrease. The intensity of the signal will continue to decrease with time. So let's continue. So that's the pre-induction decay. So for 11, inversion recovery imaging allows for, of course, this one is also a giveaway question.
B.
Yeah, nulling the signal from the given tissue. For 12, pacemakers and other critical electronic equipment should be kept outside the first line. At least I couldn't, there wasn't any way in this Google form to the 10 raised to power 4. So that was why I put that remark there. Please 10 raised to power 4 should be read as 10 exponent minus 4. Okay. So which would be our answer?
I guess, yeah.
No problem, it's good to get.
I think I went for D. I don't know.
Even if you get it, it is good to know why it is so. And the answer is actually C. I need to put some little explanation here. The answer is actually C. Let me stop this and then.
I think I went for D. 50,000 goals or so.
That was 50 goals. me stop the share. The screen one small. So this is one of the safety requirements for MRI scanner when installing the MRI. You have to make sure that at some
So I'm not
point,
seeing you.
okay, you can see.
No.
Can you see?
Yes, sir, we can see the board now.
Okay. And these are some of the things we did not discuss because of the nature of MRI, so voluminous. I guess we need to just read off from MRI
You.
safety.
I don't know. Is it my settings? I can't see. It's just blackout. Okay. This
Can you
case
see
is
now?
network.
Okay. Then.
And I can see from my hand there.
Okay.
Anybody can confirm that. Chief Akindele, can you see from your hand, sir?
I can see.
Okay.
I can't see.
No problem. We can just follow the voice, and then the recordings will be sent later. I had a problem sending it the other time. So we have for MRI, one of the safety concerns is that there is something called the 5. This is the line that demarcates a safe area and an unsafe area in MRI. I think we will have a machine there. MRI machine here. But this is the we have series of lines. So hypothetical, but the lines have been calculated such that there's an area safe here and an area that is not safe, in which you shouldn't bring in any electronic equipment or anything that will disrupt the operation of the MRI system, or even some electronics that we have. You place them close to this MRI system, that could be some problem. So the line is the 5 gauge line, assuming this is the line. So at this point, the strength of the magnetic external magnetic field of this magnet of this MRI is 75. If that line is measured so that we have the 5 gauge, then this area is safe. Whereas from here to here isn't safe. And one goes just around 10⁻⁴ Tesla. That's 0.0001 Tesla. So for that question, ought to be 5 times 10⁻⁴ Tesla. That's 5 goals. You have to give us 5 goals. Let's continue. So for 13, and a situated image, the CFS appears bright since it has what?
A short T2.
Sure.
I think a long T2. That's a long T2.
A short T2
T1.
larger than
T1 has short T1 has short TRTE. That's why water is black and fat is bright. Then in T2, because it has a longer, I think a longer T2, a longer TR and TE. That's
It
why
will have a
CS.
short T2 time for it to be brighter.
I think
Okay, that
it's
makes
Short
long.
titulation time.
Okay.
D.
Okay.
D.
D.
So D is
D.
the answer.
D.
Okay.
Not too sure of D, but I think it should be the longer T2 relaxation time on T2 because for T2 weighted images, the longer the the TE time, the brighter the image. But the shorter, the darker. It is opposed to what we have in,
T1, okay.
I think it's opposed to what we have in the T1. So the longer the T2 relaxation time. That is why for CFS, if we, of course, because it is essentially water, basically water. That is why on the, what's it called? If you want to use an inversion recovery method to null CFS, and the T is usually the TI, time of inversion is very, very long. You can see it at the end. Whereas if it's for fat has a short inversion time. Step. Whereas for CFS, we are looking at the flare. So for flare images, we have a flare sequence, the T E usually long. Not for us to go over this and this again. Whenever we see some images, some good time to look at the time given, the TE time and the TR and the TE time, so as we get used to all this. If we get used to them, there won't be any mix-up. But for 14, if the strength of the experiment by the parent within the magnetic will increase, the positional frequency of the magnetic of the patient proton will be expected to, because this is also a giveaway, expected to do what?
To increase too.
Yeah, increase. Because
Increase, yeah.
and the positional frequency omega is equal to the gyromagnetic ratio multiplied by the external magnetic field. Of course, if we now increase the external magnetic field, it means the frequency, the positional frequency will increase also. So 15. The user selectable parameters for contour selection in spin echo sequence. This is what.
It's TRT.
Any contrary opinion? Why not it? Why not? Why? This one is straightforward.
Straightforward.
It's too
I think
straightforward.
the inherent parameters are the T1, T2, flip angle, and some other thing.
The flip pumping is also a selectable parameter, kind of. Anyway, it's straightaway. TRT.
But TRTE, usually selectable, what you can select on the console also.
But you can also select the flip angle. Then adjust the flip angle. But for the spin echo, because we usually make use of the 90 degree, so that one is set there. It's only for gradient echo that you might need to change flip angle. Maybe you can acquire for 5, 10, 15, 20, and so on. So that is 16. Which parameter will give better spatial resolution? Given the slides, you have the matrix and you have the field of view.
I think I went for V.
B.
I went for B.
I actually guessed this one, but I was willing to ask what's why the slice thickness, if it controls the spatial resolution or the contrast resolution. I don't know.
Okay.
I actually guessed it to be B, though, but
Okay.
I was just thinking 2mm slice, you would be able to see things better than a larger matrix too. Should make the resolution brighter. Because the field of view is still constant for maybe all the
All of them, yeah.
all the
Okay, let's, maybe I need to stop this and use the board again. Slice thickness.
Is that an emergency? No. But
Please, we need to go. Okay.
Chiwokoro, please. Chiwokoro.
Yeah. This is not different from what we have in other imaging modalities, CT and X-ray, other conventional X-ray. The bigger the slice thickness, please, Dr. Henry, please mute. Dr. Henry.
Chief Henry Okoro, please mute.
Okay, not yet there. Okay. Maybe it's not him. Maybe he left his phone there or whatever he. No problem. I think it's better now. The slice thickness controls has a very, very big effect on the spatial resolution. Let me use this pixel. Okay, for slice thickness. Put something smaller. I know this okay. This is a matrix. You have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. This is 6 by 5. This is 1, 2,